Let's start with the big picture. The transformer is an architecture that processes all tokens in a sequence at once, instead of step-by-step like older RNNs. Its core idea is self-attention, which lets the model understand how each word relates to every other word. A strong interview answer is, the transformer uses an encoder-decoder design, built from repeated blocks that rely on self-attention, feed-forward layers, residual connections, and normalization. This structure learns long-range context efficiently and trains in parallel, which is why modern models like GPT and BERT use it. The reasoning is that self-attention gives the model a global view of the input, making meaning clearer and faster to learn. Anytime you see a system generating text, translating language, or summarizing documents, you're seeing the benefits of this architecture. Now, let's make self-attention simple. Each token becomes 3 vectors, called query, key, and value. Queries compare with keys to measure how strongly words relate to one another. Those scores are scaled, passed through Softmax, and turned into clean attention weights. The model uses those weights to blend the value vectors, so each token gains context from the whole sequence. A clear interview answer is, self-attention helps each token focus on the most relevant tokens, allowing the model to build rich meaning even across long sentences. The reasoning is that every word can directly look at every other word, so the model never loses track of important relationships. If an interviewer goes deeper, you can explain that scaling keeps training stable and Softmax turns raw scores into smooth, usable weights. Now let's put the pieces together. The encoder is a stack of identical blocks, each containing multi-head attention and feed-forward layers with residuals and normalization. Its job is to understand the input deeply. The decoder also uses blocks, but it adds masked attention, so it generates outputs one step at a time without cheating, plus encoder-decoder attention to link its predictions back to the input. A strong interview answer is, the encoder builds contextual representations, and the decoder uses them to produce coherent output. Multi-head attention lets the model capture different patterns in parallel, while feed-forward layers refine each token's meaning. Residual connections and normalization keep training stable and help the model scale to great depth. This entire structure is what allows transformers to learn complex relationships quickly and reliably. Interviewers often dig deeper, so here are natural ways to respond. If they ask why multi-head attention matters, explain that each head learns a different type of pattern, such as syntax or long-range meaning. If they ask about positional encoding, say that since transformers process tokens in parallel, they need a way to represent order, using smooth, sine, and cosine signals. If they ask why we scale dot products, the answer is stability during training. When comparing transformers to RNNs, highlight faster, parallel training and stronger long-range context. And if they ask about real-world usage, point to GPT for generation, BERT for understanding, and vision transformers for image tasks. These answers show that you understand both the mechanics and the practical value of the architecture. Great job learning today. If this helped you feel clearer or more confident for your AI or ML interviews, tap like so more learners can find you. If you want simple guidance for every interview topic, subscribe so you never miss the next lesson. You can share your questions in the comments. I read them, and they help me choose what to teach next. And if you know someone preparing for interviews, feel free to share this with them. Keep going. You're improving with every step. I'm here to help you grow.